Good day, everyone. My name is Karen Neri. I'm a PhD student of nanoscience and micro-nanotechnologies at the Instituto Politécnico Nacional in Mexico City. And today I will be presenting the work titled MnO Zinc Oxide Zinc Thin Film Heterostructure for Adaptive Electronics. For the introduction, we have that as the reduction of the scale of the technology reaches the prediction of Moore's law, an approach for new ways of processing information is through adaptive electronics, where an electronic device can be designed with different properties and incorporation of internal states that are capable of reconfiguration. Thus, an external stimulus will self-adjust the parameters of those properties to carry out certain operations. An MnO zinc oxide zinc heterostructure is synthesized where the use of internal states allows new operating modes. For the experimental procedure, we have the glass substrate cleaning, the manganese target with this sputtering, the characterization of that layer, zinc oxide and zinc targets with co-sputtering and the characterization of that layer also, the final structure which is zinc oxide zinc on top of MnO, and finally the electrical characterization and the internal states. This is the structure that was made. For the results and discussion, we have the X-ray diffraction. We have a plane 111 that corresponds to MnO and 101 for the manganese. Now for the zinc oxide, we found the plane 002 and the crystal size is 10.3 for the MnO, 4.8 for the manganese, and 16.14 for the zinc oxide. Now for the band gap determination and band diagram model, we found a band gap of 3.3 electron volts for the MnO, and for the oxide zinc with zinc, we found two values, 3.3 that is characteristic of the zinc oxide, and 3.1 that we believe is related to the interstitial zinc that is incorporated in the co-sputtering. This is a representation of the band diagram. We have the MnO, 3.3 electron volts, and the oxide zinc, where the MnO is a p-type semiconductor and the zinc oxide zinc is an n-type semiconductor. The reconfigurable device demonstration in time response and IV curve signals. IV is current voltage signals. We have this circuit where we have a sinusoidal signal of 4 volts, a resistor of 1 kilo ohms, and the structure where the MnO is channel X and the zinc oxide zinc is the channel Y. At 1 kilohertz, we found a rectification state of the structure, and we see here in the IV curve also the rectification curve. And we have this model where the diode is the one functioning. The internal structure is represented by this circuit. At 10 kilohertz, we found also a rectification state, but an increase in the IV curve is represented here by a capacitor. At 100 kilohertz, we found that the rectification state is distorted and we have a more capacitive state represented here in the as red in the circuit. At 300 kilohertz, we found that rectification state does no longer exist and the capacitive effect is larger, but we found a cross in the IV curve that is represented by an inductor here in the circuit, and also at 800 kilohertz, we see that cross in the hysteresis of the curve. That cross can be described as a pinch hysteresis, and that effect is related to the inductor, as we can see here in the equivalent circuit of the heterostructure. For the internal states, we have that a barrier is formed at the interface between the MnO and zinc oxide zinc. This heterojunction behaves as a diode, as a half-wave rectifier at 100 Hz, 1 kHz, and 10 kHz. For 100 kHz to 1 MHz, the rectification behavior changes due to the rise of the frequency, and the states reflect a transformation of the signal. The space charge region increases as the frequency rises. The hysteresis of the IV curves is directly related to this change. The heterojunction does not degrade with the changes in frequency, and the states are repeatable over the spectrum of 100 Hz and 1 MHz. Both the external stimulus of the frequency and the stable and repeatable signals of each state allow us to determine that the MnO zinc oxide zinc heterostructure can be deemed as a reconfigurable and in use in adaptive electronics. For the conclusion, we have that the properties of MnO and zinc oxide zinc in the thin films are obtained by magnetron sputtering and co-sputtering, respectively. A PN heterojunction was formed with these two materials, and the interface of the heterostructure is used as a transfer function. Using an oscilloscope and a signal generator, it's possible to observe the time response signals and the IV curves at the heterojunction. The performance of the device under the frequencies in the range of 100 to 1 MHz show the presence of reconfigurability. The zinc oxide zinc MnO glass structure is reproducible and stable. The states are stable and can be achieved repeatably under a signal of 4 V or less in the input. Finally, an MnO zinc oxide zinc heterostructure is of great interest for oxide electronics and can be used in adaptive device application using reconfigurability through frequencies and internal states as an option to reduce the number of components connections in a system. We have the authors here, and if you have any question, please contact me at my email. Thank you for your attention.